Start recording, 25 frames per second, CPU is okay. Start streaming. Start watching. It should be streaming, I should be live. And I am live. So, welcome to part 2 of constructing a DMX control DC motor. Why part 2, although there's no part 1 on the stream? This is simply because I didn't enable recording and recording the previous streams. I did a previous stream last week, but yeah, this option wasn't enabled, so the recorded stream was not there. But I'll explain it. I'll have a brief overview about the project. I started last week. I worked for it for about three hours. And as the title says, DMX control DC motor. And normally I should be able to hear myself. Let me check my own audio. Playback, that works. So, DMX control DC motor. So I have a project in the club I am working in. Just to help. And this is where there's a clock there. Maybe I think I have a bit. Let me check. Let me look for it. Data projects. No, not here. Pictures. Overview picture from the back, but I want one from the front. That should be somewhere in data, pictures. Clock. No. I don't have a picture of it. Okay, so it's not a very good picture, but at least it is a picture. Let me switch to screen view. Yeah, so this is a very large clock which is on top of where the DJ mixes. And there are dials on there. The clock doesn't work as clock anymore, but we can make some kind of animations with it. For now, what exists is that this clock are rotating with a fixed speed. It's just a motor connected to a USB power bank, and it turns around. It makes a nice effect. So if you synchronize the stroboscope with it, you can have the time really slowly going forwards and then really fast going forward. So it makes a good effect. What also exists is that, let me show you the back. This is on the back, so this is the back view of the clock, and you see it is quite large. What also works is that this clock turns around. We see here this is a AC motor, and it turns around the clock, and this is why it is operated by a USB power bank, because we can't have cables from the clock going somewhere providing power. So the USB power bank is providing clock here. Now what I want to do is two things first. First, this is the first part of the project, is having just a DC controlled DMX motor. So this way we can control the front, the dials on the clock, using DMX. And we can set the speed. So what is DMX? Let's go back to the bench. DMX is used in the lighting industry. If you ever went to a club or something like that, you probably would have seen something which looks like this. This is a very cheap one, but it is a light with plenty of LEDs, and it is very often used in the lighting industry, and DMX is a way to control the light. So this way you can somehow change the color of the light depending on the music and depending on the rhythm, depending on your mood, and you can have really good light shows. You can also have other fixtures like moving heads or smoke machines or things like that. And when you want to remote control it, you always, or the standards in this industry is using DMX. DMX, as you can see, we have ports here. DMX in, DMX out. I'll show you here. So DMX in, DMX out. And this allows you to connect with a cable on the DMX in and remotely control this, so you can change the color from somewhere else remotely. And then you have a DMX out because you can actually chain these fixtures and have plenty of lights in a chain, and then you can control all the lights just using one DMX cable. Now you see here these are 3 pins. So DMX on in the details. Let me just switch a bit the volume down because I have too much feedback on my own headset. Yeah. So DMX, how DMX works. You see here 3 pins. Actually, so the connector looks very much like an XLR connector. It is actually an XLR connector with 3 pins. 3 pins is actually not recommended. I even say it's forbidden. Yeah, it's forbidden by the DMX standard, or the one which makes the DMX standard, but it is very often used because it is cheaper, and it is good enough because you only have actually 2 pins on the, you only use 2 pins on the DMX on the XLR 3 pins connector. The one which is specified is the one with 5 pins, and you have then Ethernet or other kind of cables. 3 pins is forbidden, but still, although it is forbidden, it is very widespread, and almost everyone uses this one if it's not in the very professional lighting industry. The problem, so it is enough because you only need 2 pins. I'll explain the electrical protocol afterwards. But it is forbidden because the XLR cables with the 2 pins are almost exactly the same than the audio cables. But you don't want to connect DMX on audio gear or audio gear on DMX. It could damage one or the other, although it is very unlikely. It could do it. And the other thing is that this cable has a kind of impedance because it is a differential protocol. I'll come to that. The cable should have an impedance of around 120 or 100, something like that, 120 or 100 ohms. And audio cables don't have this control impedance. DMX cable have it. And this allows you to have an to keep the integrity on the signal, although you have multiple drops. Don't forget at the end of your chain, because you can chain plenty of them, you have to put a terminator, a 120 ohm terminator. Except if it's not really chained but forwarded, but that's another point. You will know what I mean if you work with it. So you don't need me for the explanation. So this is DMX. Now, what I want to do is use DMX for the DC motor. The problem is that, as we see, we cannot have cables on the clock, on the back of the clock, because the clock is spinning, and the cables would just tangle themselves. So we need to do over the air. There is no real, although there is an alternative to DMX, which is called E1.31, which is simply DMX. Oh, I wanted to talk about before we talk about the wireless version, let's talk about the wired version. DMX. DMX just uses 2 pins. You could use the 3rd pin for ground, but it is not required because you just need channel A and channel B somehow, signal A and signal P, or plus and minus. It is a differential protocol. So what matters is one signal is higher, or one voltage is higher than the other, or if the other voltage is higher than the other. I think it's 500 millivolts differences, but it doesn't matter how much higher it is compared to ground. It is just from one to the other, and I think it's 500 millivolts. And the protocol they use is called RS485, which is a serial protocol, like you probably heard of RS-232 or UART. So UART is a CMOS protocol, a CMOS level, 0 to 3 volts or 0 to 5 volts. RS-232 is the same protocol, but on an electrical different one. It's between minus 12 volts and plus 12 volts. And RS-485 is just somehow the same thing from the transmission point of view, but just electrically it's different. It's a different protocol. So from the logical level, it's just a serial stream. It actually sends 513 bytes and then a break. And the first byte of the 530 bytes tell if it's DMX message for light control or something else, or for controls. And then you have 512 bytes of data. This is also why the normal term, the exact term is not DMX, but DMX 512. You have 512 bytes. You always program the fixture to listen to which byte, they call it channel, it wants to receive the data coming from. So if I now set it to channel 1, out of this 512 bytes of data, it will take number 1 and then plenty of others, because we have red. Maybe if I connect it to have power somewhere here. Up, yeah. We have red, green, blue, white. So we have 4 channels. One channel for the red, second blue, third green, and the last one white. This is at the minimum. So if we want to control the 3 colors of light differently, we need at least 4 bytes. This is why if we program to channel 1, we will have channel 1, 2, 3, and 4, which are used to control this light fixture. But it's not only this. They have even more channels. I think there are 2 more. One to control the mode or how fast it blinks. One to control the overall dimming. I don't remember exactly, but you have generally more than 4 channels. The pain with DMX is that you have to program all fixture and say, okay, you start with channel 1, so you listen to the first byte, and then you have to know that this one listen to 6 following, and then you have to program the other fixture to program to start at channel 7 or channel 8 and so on. It's a bit of a pain to program them. There's another protocol which allows you to remotely program them, but by far the most used is just fixed program. So when you program it once, you have somehow to write it, that it is programmed or what channel it uses, and then you never touch it again. And you hope that no one touches it and messes with your setup. If you have moving fixtures, then it's a pain because you always have to reprogram everything. So this was DMX. Now we want, or DMX 512. We don't want to have wires. We want it to do wirelessly. There is a DMX alternative which, instead of using this RS-485 interface, electrical interface, is sent over Ethernet. This is called E1.31, and it is simply the same stream of data, the 513 bytes, sent using UDP messages over Ethernet network. That's basically all. So what we can do is that instead of using Ethernet, the cable for unwired network, we can use Ethernet like it's sent all over Wi-Fi. So it would be wireless. There is a kind of an issue because these messages are broadcasted to a lot of fixtures. Now, if you have Wi-Fi clients, not every access point supports multicasting or broadcasting to all devices at once. First, it could be slow if it supports it, and if it doesn't support it, it's even slower because it needs to send the packets to all individual devices. But it still exists and it still works. And this is the method that is used in the club I'm working for. They have a lot of fixtures control over DMX actually. Yeah, here. If you look at the picture, you see some kind of light here on the side, on the top right side. And this blue light is controlled over this over Wi-Fi using E1.31. Because it is this way, I need also to use Wi-Fi, and because it will be Wi-Fi, it will be really easy to control remotely this clock, and it doesn't need any cable. This is the project I'm working on, and these are all the parts we will have or we will use. Can I go up? These are all the parts we will use for that. I always keep my projects, or actually all my electrical parts, in this kind of transparent boxes. These are, as you can see, these are ice boxes. Over the time, and they're very good because they're relatively inexpensive and you can collect them over years, and I have plenty of them. They're translucent, you see what's inside, they're robust, they're cheap, and what's very useful, as I said, is that over the years you can buy them and they always almost have all the same format. You see here on the side, I tried different formats, and the end format is this one, and I have most of my electronic parts in these ones. In these ones I just keep other spare parts which I don't use very often. So what's in this box? What's everything that we will use? Because it needs to be remotely operated without cables, we need power. And I just took kind of a battery, which I collected from one of the spare phones I don't use anymore. This is just a lithium polymer battery. We need to be able to charge it, and this is why we have this module. This is, not sure if it makes the focus. This is a two-part module. Here we have a TP5046, I think. This is a lithium polymer charger, and then on the side we have battery protection, so it doesn't overcharge, it doesn't over discharge, and it doesn't draw too much current. This will be able to charge the battery and protect the battery, because not all batteries have an internal protection. Sometimes they do, but since we don't know if this one has or not a PCB which does the protection, we will use an external protection. What we also have is, for the wireless interface, I use this board. This is an ESP8266 based board. I think it's a Wemos clone or a Node MCU. I don't really care what it clones. I just care that it is an ESP8266 and it has some flash, I think 32 megabits, so 4 megabytes of flash, and you can flash it over serial. I don't really like ESP8266. I'm more fond of bare metal programming, which this doesn't really allow because not all the registers are defined, and it is a bit complex, but this club I'm working on is using Wi-Fi, and for Wi-Fi this is the cheapest and good enough solution. I did write a small code for it already, and this will come later to it. So I will have to use Arduino and a lot of external libraries, or a couple of external libraries, because I don't want to spend too much time on it, and it's good enough for the job it will do. Then we have here, this is, actually this is the same as this. This is a DRV8233, and it is a dual H bridge. This is used to control motors. Either you control two separate motors or you can control one stepper motors. I've already presented it on one of the videos. I think it's the, which video was it? The grill bomb. I talked about this device to control DC motors, and this is what we will use here. This is also what we did in the previous episode, which is not recorded, and the video is buggy. Video, come back. This capture card. Okay, the video is back. This is what I've done in the last episode, which is not recorded. I've programmed the I've shown how this works, and we were able to turn this DC motor, which you see here. That's the DC motor. This is a boost converter, a step-up voltage converter, whatever you want to call it. And the use for that is that, so this module requires also power to be operated. It's because the logic here is based on 3.3 volts. We have a voltage regulator right there, and because it uses 3.3 volts, maybe I just should zoom. Not sure why it doesn't do an autofocus, but yeah. Since this here is a low voltage regulator for 3.3 volt, so because this operates at 3.3 volt, and it is kind of a pain because it is not 5 volt compatible or tolerant. Because it is 3.3 volt, anything with 3.3 volt and 0.3 volts above works. This is why this LiPo battery just fits on it. It is between, this nominal voltage is 3.7 volts, but it is between 3.3 and 4.2 volts. You shouldn't drain lower than 4.2 volts, and actually this battery protection will take care of you not draining too much the battery. So this will provide power to this, but the disadvantage of the battery is that the voltage lowers as you deplete the energy. And what we do want to have is a very synchronous clock, or a very steady clock turn or dial turn, because we want to make synchronous flashes with dials. So we don't want the dial to change over time the speed. We want to have a constant speed. So we need a constant voltage. This boost converter will provide a constant voltage because it boosts up to a constant voltage you set. The second advantage is that you can go above 4.2 volts because it boosts the voltages. We could add 5 volts or 9 volts, and this will be able, with this we will be able to set the maximum speed of the device. And then using the PWM on here, we will control the stepping speed in the end. And because we can change, it's an adjustable voltage booster, because we can change the end fixed voltage, we can also be sure that the PWM we are using, or the duty cycle of the PWM, covers the whole range of the clock of the dial speed. This is why we have this voltage booster. Set the maximum speed, have high speed if we want to, and be able to use the whole range for the PWM. So these are almost all devices. Then I will also have an LED. This is just an RGB LED, and it will allow us to show if there is an error, if there is power, if nothing is activated, and so on. We have a switch because we want to cut off the power so it doesn't drain the battery when it's not operated. This device uses Wi-Fi. Wi-Fi uses a lot of energy. This battery will be really fast depleted in a couple of days. Yeah, I would say even in one day or in a couple of days, if we always have it turning. So we can switch the clock off, not remotely, but we can switch the clock off using a button, then recharge the battery and keep it switched off when we don't use it, and save the battery. And then we have this project box. This is a very common box. I have plenty of them, and I do most of my projects in these project boxes. You can find them on AliExpress. I think it's 55 times 25 times 35 millimeters. I don't know, but if you look for project boxes, you will find them on AliExpress. And they're spacious enough to have all the projects inside and still robust. And then I have my custom designed pair of boards we can put inside where the whole match to the box, and this way we can put all the components in there. But before I do my hardwired or hard soldered boxes, I always do on the breadboard because it is easy to see if there's a component missing or not. This is why we always also have the setup, because last week I already started working on it. What is working here? We have power coming from the power supply there, which you can see, which I could show you. Let me switch the input. Does it work? Yes, it does. So here we have the power supply. This power supply just provides 5 volts. We could set it to follow 2 volts like the battery would, but we would just 5 volts for ease. To the board. Switch back. And once we have our 5 volts, it provides power to this. It doesn't like. has issues keeping with the HDMI multiplexer. So once we have 5 volts, we have Ethernet, we have Wi-Fi, and we can control it. Then we have here a switch which actually cuts the power to this board and to this board, but will also cut power to this board in the end. This is just so I don't have to press on the button all the time if I want to switch off or test something. Switch off the power supply, I can just cut the power here. And it will be in the end box, like I've explained. Then we have this board, which is also operated by this. This is powered, actually it is powered by this voltage booster. Now it is set for 6 volts, and it will operate here. But the I/O pins, which control the speed of the motor, are not the same voltage levels as the motor pins. So in the output, what you see on these 2 plugs, now I can zoom because most of the time I will be there. Here we have connections to the motor. It goes right there. This is just an example DC motor. It's not the actual motor which is on the clock. It's to see if everything works. Here we will have an output of 6 volts modulated to the input PWM pin, which is right. I think it's, which one is it? I think it's these 2 first channels. Yeah, I think it's these 2 channels. And there's then this pin which puts this device to sleep or not sleep. Can I say, yeah, focus on here, to sleep or not sleep. And here on the inputs to control the motor, we just have a PWM signal, and by changing the pulse width, so the duty cycle, the pulse width, the duty cycle within the frequency, we can change how fast the motor spins. This is where we stopped last week. We didn't test the PWM. We tested that this device boots up, we have power, this is outputting 6 volts, this is working as as driver, and we tested it as driver just with power, not with PWM, and it was able to turn this device. So let's check if it works with signal outputted from here, which is output there. Up, and this is where we continue today. You might wonder also on the stream why there's only 720p available resolution. This is simply because my internet doesn't allow me to stream more. I don't have enough bandwidth, and it is impossible. It's just it's not, except if I would have LTE, but this is very unstable. I cannot have more than this at home. I do have a 100 megabits contract, but this is not reached. I only have 2 megabytes download, and in Berlin, I am in Berlin, fiber doesn't exist, and the operator has a very shady network, which is some kind of legacy, and since a couple of months I am not able to have the 100 megabits which they provide me in the contract, and none of the others would be able to do it. And this is why for now it is in 720p, but should be enough if you have it in a corner of your window. Oh, now let's continue the part 2 and see how far we'll come today with this mini project. So last time I wanted to check if the PWM output works. So let's switch on the power. Power is on. It draws 70 milliamp, 200 milliamp. This is normal. This is used. This is the average consumption or the power consumption from this device. This for now doesn't draw anything. And we have the output here, and if we put to sleep, so normally this is sleep, this is not sleep, so we should be able to already turn the device, but it is not turning, so maybe here there's no PWM output. And I know why there's no PVM output. I've showed something last week. So I have a mini firmware here, which just for the demo is able to send some PVM data, but it already accepts DMX data. How does DMX work? We will see it. I'll show you on the computer. So let's switch to the screen. And here we see the summary. Title, we have all, this is what we did last week. We have all parts, we soldered the main power supply, we tested the motor with the voltage booster, and we tested the motor with the DRV 8833, which is a dual H-bridge driver. And now, so this is, we can get rid of this. Let me start my DMX controller. Let me check if actually the sound still works. Sound on. Yep, it does work. Analog stereo HD should work here. Output devices, speakers, playback. Does it work? I don't hear anything. Test. My recording setup says it works, but I don't hear anything. HDMI. I did hear a couple of things a couple of minutes ago. Now I hear nothing. Okay, I hear something, but from the PC. So, I think the microphone works. Yeah, it just doesn't play it on the right channel. Oh, it works. So, DMX, how do you control DMX? You have to send the data to this device over the network. For that, there are plenty of professional, not professional software. I'm not too much of a professional for that. I don't actually do control DMX devices. I just build gadgets. And for this case, we will, for this setup to test everything, we will use a software which is called QLC+. This is QLC+. First, we need to load the fixtures. Open, I do have the fixtures here. Fixtures, we've talked about, so fixtures are kind of devices in the DMX chain. These are actually clock dials, not clock fingers. So we've already talked that in a fixture, generally, you could have multiple DMX outputs. This is, or DMX chains. This is what you call a universe in the DMX world. Then, within the universe, you have fixtures, like we would have our lights. In the fixture, what is important is that you tell how many channels you have. If we edit the fixture, we can see that it starts at channel 1. This is actually the device address. And here you see the starting address, which you have to program in the device. And then we use 2 channels because we want to control the speed. Why do I use 2 channels and not just 1? Because 1 byte would be enough to control the speed of the rotating things. Now I have 2 bytes. This is simply because we have a 10-bit PVM, and I want to use the full 10 bits of the PVM to precisely control the dial speeds. And this allows to fine-tune the speed of the motor, so you can really have a good synchronization with flashes. Now, we have 2 channels here, so we have 2 times 8 bits. We have 16 bits in total. In these 16 bits, we have 10 bits of PVM data, the end speed, and then we will have 1 bit which is used to control if it goes forward or clockwise or backwards anti-clockwise. So in the end, we use 11 bits out of these 16 bits, but we have to use 2 channels because because one channel of 8-bit wouldn't be enough. And this is actually, you cannot describe this in the DMX universe or in the fixture. You really have to know it. And I will have to tell the one which operates this that this is how you use the two true channels. These channels miss this, these other channels means this. And you always have this with DMX fixtures. You always need an external description telling what does each channel. Sometimes it's paper, sometimes you have to try it out, sometimes you note it. This is a pain. There is a kind of an extension protocol which allows you to add some more information, but by far the default is that the operator of the DMX chain or the operator of the fixtures has to know which channel does what. So here we have one fixture. This will just be the, let's rename to clock dials. Clock dials. Up. Save it. Here we have the fixture. Now what we have is a virtual console. Simple desk here. The simple desk. I've told you that DMX is a string of 512 bytes, and this is where we have the 512 bytes. First byte, second byte, third byte, and so on. And here we have 512 out of these. We only use the two first ones because in the fixture I told that the address is address number 1 and that it uses 2 channels. And here we see address range 1, 2. This is why in the simple desk I only care about these 2 first channels. This way you can set the value which will be sent over the DMX stream. Now, the other important thing is how you output this device, or how you output this stream. Normally you could have DMX, some like DMX USB, so you can use this XLR plugs. In our case, we will use E1.31, so it will be DMX over Ethernet, sending just UDP packets, and you see here I'm choosing this network for it to send data on, and I set it as output. And now, if I press on play, I'll put the motor somewhere safe in case it does spin. I will still put it to sleep. So now this should be to sleep. And if I now press play, we should have some data output on the network. Let's go back to the console. For now it's 0. Let's have it a bit higher and see back on the bench if this does work. So now I'm connecting, this is connecting, there should be a PWM output. If I remember correctly, it should be on D1. We could test it using the oscilloscope if it doesn't work. So power is connected, we don't have, and it's not turning, which is good. So the sleep on the chip does still work. Up. On zoom, so we have a better overview of everything. Up. It doesn't short, and now if I enable it, it should actually spin. It does spin. To see a motor spinning, you do see the motor, but you don't see it spinning, and you will not hear it because you will only hear my voice. To see the motor spinning, I will add some tape on top of it. Up. Now, if I remove the sleep mode on the chip, you see it is spinning, so it does work. And if I change anomaly, I am able to change the speed. And it should go slower. It does go slower, but not a lot. This should actually switch it off now. 0, 0 should be switched off. But it is not switched off. So I have to control why the data is not incoming. Let me read the data from the serial stream. I think I'm sending it as output. So this is connected. Okay, it doesn't receive any data, or it doesn't show me anything over serial. Let's reset the device. What is the reset button? The reset button. This is the reset button. Let's put it to sleep. Just too noisy. What you see is that this is on when as soon as I unplug it, it goes to sleep. This is because the device has an internal pull-down resistor. So by default, if you don't connect anything, if you leave it floating, it does pull the device down. It does pull the pin down and switches off the output. So I am connected over USB 0. It should work. Does it say something over USB that there's not enough bandwidth or something like that? No, it does not. Let me show you what I'm trying to do. No, just file of directory. Okay. Disconnect, reconnect the cable. I can use a longer cable if this doesn't work. Okay, it doesn't work on this hub. Let me get a longer USB cable. Okay, this USB cable does not work. I do have another one somewhere lying around. I do have USB issues currently because I have lots of devices. Actually, I don't have that many devices, but streaming, having two video feeds, the two video feeds are over USB using USB grabbers, USB capture cards, and video data is very heavy on the USB bus. So I am missing packets. So now this is attached. Okay. Can I see that it is booting and working? No, it is either not or I don't see it because my USB bus, and I only have one USB bus on the whole laptop because the USB bus does nothing. So either this is stuck it should show data when it is booting. It is on. Now if I switch it off, it only has power from the USB now. No. Does it? Is it because my USB network is too crowded? Oh, now we have it. Motor speed 0. Okay, now you see that it does work. You don't see very much of it because the font is very small for the stream. Yeah, but this is the output I have from the device, so it does work when it is not connected. Now it is connected. Do I still see the stream? Yeah, connected to the Wi-Fi. And if I change the speed, we should see the speed changing in here with some latency. Yes, we do see but we do lose a lot of packages. So yeah, my USB bus is just too crowded and we don't see a lot of things, but it should have data and it should receive data. So if I switch, let me turn it off. And if I now turn this on, the motor should be, yes. Wait, I have to turn power on. This was a bit too much. power supply. So now it is off. It is not turning, and if I increase it, it should turn slowly. Here there is not enough power. I hear the motor beeping. Come on. Ah, now it turns. But it doesn't turn fast. So this works. So I really need, okay, now I'm 35, but this works. And if I, again, switch it low, after some time, it should go back to 0 and stop turning. But it doesn't go to 0. No, it does go to 0. There's just a very high latency. And the very high latency is very probably because my USB network is completely overcrowded. What I could do is, does this work? Maybe the stream will be blocked, so we don't do it for now. We will use it as is. Yes, we will use it this way for now. My USB network is crowded and I need to find a solution at some point. And I'm working on it, but it takes time. So this works. We do it clockwise, and we could actually do it also counterclockwise, and for that we have the second signal. D0 should be the counterclockwise signal. So let's get some cables. There are tons of things I don't require from here anymore. This. Let's put it back where they belong. This is where I took the motor from. This is my motor box. Let's put it here. Here we have cables. This I will require for later, so let's leave it on the bench. And what I need is here, DuPont cables or wire cables, male to male. This bag mainly. Up. And let's connect. Train should connect it this way. And let's switch the power off. Put the motor to sleep. We still see that this device is connected over USB. Let me disconnect it. Oh, let's leave it from there for now. I'll remove this cable. You will be right there. You will be connected right here. What you could do, instead of having wires directly connected from the driver, H driver, to the ESP, is having inline resistors, inline protection resistors, something like 100 ohm or 200 ohm, something like that. We don't only need voltage, logic level input with not a lot of current. And what this would allow to do is protect this ESP. Here the pins are just 3.3 volt compatible. They are not 5 volt tolerant. So, and here we provide it with 6 volts from the voltage booster. So what could happen is that we fry this because for, I don't know, unknown reason, it gets too warm, it gets stuck, any kind of reason. If this gets fried, the 6 volts could feed back in to the gate if it's not done well, if it's not protected. We never know. Could feed back in the gate, and then we have 6 volts on the 3.3 volt pins. And this would fry at least the pins of the ESP8266 if it doesn't have clamping diodes, or even if after sometimes it will fry them. And it could also completely fry the ESP. And using inline resistors, we could protect it. And I will probably add inline resistors at the end, but for now, this is just breadboard prototype. And I will just leave it like this. So we have the two things. I need to extend the firmware. The firmware for now just gets some DMX data and puts a PWM signal out using D0 and D1. What I want to do is being able also to completely switching off using this sleep input pin, and also to control the LED to indicate the status. Does it receive data? Is it on? Is there an error? And so on. But I will not show, I will try to not show on the stream too much software or firmware coding, because I find it boring. It takes too much time. This is mainly a stream for building hardware. And firmware, sometimes, yeah, I don't find firmware or coding in general very interesting to watch. Now we are connected here, so now if we enable it, this is enabled. We should be able to see it clockwise, turning clockwise and counterclockwise. Let's try again to send some data. 64. Should be turning soon. It is turning. And then if I go above 128, it should be turning the other way around. Is it turning the other way around? Doesn't seem so. Ah, but it says counterclockwise. I don't know if it does actually counterclockwise. At 256, 55, it should be almost not turning counterclockwise. Ah, the USB bus is too overloaded. That's a pain. So I don't see in real time what everything is done. Okay, so it doesn't turn. Now if I go a tiny bit back, it should be able to send the data. It should be able to turn counterclockwise. Ah, and I think the video stream is also sometimes broken because the USB bus is too overloaded. Let me try to fix the USB video. USB video doesn't work again. Come on, USB video. So, this is actually a good overview of the status. This is what is working now. I will stop the stream. So this is the overview part. I will stop the stream and continue in, I don't know, 30 minutes or something like that, once I've kind of tried to fix this USB overload issue by disconnecting, reconnecting, everything a different way, and maybe working a bit on the firmware so it doesn't bore you too much. Once I've done that, I will be back today on the stream. So see you later and enjoy for now.